And we're back. It's time to sort it out with Mr. Swartout. Here is a problem involving power. So here we have Billy on a hill, and I suppose you can't really see the diagram too well, but we have Billy here, and then we have poles that are spaced 10 meters apart up this hill. And what we want to solve for is the power that is needed. So what we're going to do is first we're going to go ahead and time him. So what you do is you click start motion, and then he's pulled up the hill by this cable. Then if you count the poles, you can let him go, and then based on the number of poles that he passes, put that in as the distance, delta x. And then whatever the time is, we can put here. So the velocity will be the change in position divided by the change in time. So that will give you the velocity. Then power. Now power, remember, is the rate that work is being done. And then work is FD cosine theta. And then that is all divided by the time. Now this is kind of cool. In this particular problem, the force is being applied up the hill, and Billy's displacement is also up the hill. So what that means is that there is no angle between the displacement and the application of the force, so that theta would be 0 in this case. Even though we're on a hill, the cable is pulling this way, which is exactly parallel to Billy's displacement. So that means the angle is 0. Then distance divided by time, we know that. That is actually velocity, isn't it? So power then would be the force times the velocity. Okay, then what would be the force? In this case, we're doing a incline. So if you remember how to break that force of gravity into components, force gravity parallel to the hill is mg sine theta. So the force applied here would be mass of Billy and the sled, little g where this takes place, sine theta, that's where we use the angle of the hill, and then the velocity, which we found in the first part. So that's how we can get the power in this case.